Okay, so now let's look at those double integral problems. So you evaluate this double integral xy squared dA, and the region here is x is from 0 to 1, y is from 0 to 2. As you can see, this region is a rectangular region. So based on the Fubini theorem, actually we can start from any part, right? From any part. So we can write from 0 to 2, and then from 0 to 1, xy squared, and then dx dy. Or we can write from 0 to 1, and then from 0 to 2, xy squared, and then dy dx. I mean, the Fubini theorem said that if the region is a rectangular shape, and then so the order actually is interchangeable. So we can focus on the first one that give us which is x squared over 2 y squared, right? 0 to 1, and then dy. So this will give you, actually it's half square, right? So it's and then this will become into y cubed over 6 evaluated from 0 to 2. That is 8 over 6 or 4 over 3. Okay, that's the first problem. Very simple. The second way is express the area of the region bounded by the given lines as an iterated double integrals. So as you can see that the area of the region, if you write it out in terms of a double integral, which is into this way, right? So let's draw this first. So x equals 0, y equals 2x right here, and then x equals 2, right? So this is 2. So this is the region what we are looking for. This is y equals 2x. And turns out this is the coordinates of this point is going to be 2, 4. So I can label here is 4. It really depends on, whether you want to express in terms of y and then x or vice versa. Okay, so, if we set it up, constructed a vertical cross section, as you can see that y is bounded above by 2x, bounded below by 0, so it's going to be 0 to 2x dy, right? And then x is from 0 to 2, so from 0 to 2 dx. So that's one way to express this area. Or you can construct it horizontally, right? So in this case, x is bounded by 2, bounded below by y over 2, right? So if you solve x, so it's going to be from y over 2 to 2, and then dx, and then our y actually from 0 to 4, right? So it's from 0 to 4 dy. Okay, so it's also still the same thing. That's those two problems. The next one is change our Cartesian integrals into an equivalent polar integral, and then starting to do the evaluation. So the regular Cartesian integral, and then if you're trying to interchange it into the polar one, so you're gonna need r cosine theta to substitute x, y equals r sine of theta, right? and also r d theta, and also this r, so you're gonna have the g1 theta, g2 theta, and then this theta is from alpha to beta. Okay, so in other words, to change the Cartesian integral into the equivalent polar integral, you basically need to do two steps. The first step, you need to substitute x and y in terms of r and theta, which is here. And the second thing is, keep in mind that the iterated double integral for polar is going to be r dr d theta. And also lastly, you need to find the correct function in terms of theta for our r, and also the correct the range of the theta, which generally we denote from alpha to beta. Okay. So so for this problem, the easy part is here, it's give us is equal to 1. Okay, is equal to 1. So basically we are actually looking for the area, right? The area of this region. Let's take a look at this. Our y is bounded below by 0, above by this. So y is greater or equal than 0, less or equal than square root of 4 minus x squared. And also x is between negative 2 to 2. So if you draw it out, turns out you will see that this actually is going to be the half of the circle. And then this is x squared plus y squared equals 4. Okay, equals 4. And then, so now things becomes pretty straightforward, because from here, what we can read here is, in other words, if you randomly draw an array, so you can see that it's starting from here, and then it escapes when it touches through this circle here. And also the theta is ranging from 0 to pi, right? From 0 to pi. And of course, x squared plus y squared equals 4. If you convert it into polar, that's going to be r squared equals 4. In other words, r equals 2, right? R equals 2. So, put all these pieces together, the equivalent polar integral is going to become into from 0 to pi, from 0 to 2, and then r dr d theta, okay, dr d theta. And of course, you can evaluate this. So it's going to be r squared over 2 from 0 to 2, from 0 to pi, d theta. So it turns out this is going to give us is 2 d theta, and then this give us is going to be 2 of pi, which we know that the radius of this overall the circle is 2, so the area of the half circle, which is pi r squared over 2, which is also is 2 pi, right? So yeah, this is one of the examples related to the double integral.